I didn't actually know what conformal field theory was at the time I was writing down these definitions. All the claims you see that vertex operators came from conformal field theory are just wrong. Part of the problem was there seemed to be no way to, it was just relating these two things that had nothing to do with each other. So it was not clear how one could even get started on it.
Welcome everyone to the Cartesian Cafe. I am your host, Tim Nguyen. Today, we're very lucky to have Richard Borcherds here with us. Richard is a mathematician and professor at University of California Berkeley, known for his work on lattices, group theory, and infinite dimensional algebras. His numerous accolades include being awarded the Fields Medal in 1998 and being elected a Fellow of the American Mathematical Society and the National Academy of Sciences. Welcome, Richard. How are you doing today?
Oh, hi. Doing great so far.
Great. It's such an honor for the Cartesian Cafe to be interviewing its first Fields medalist. Also an honor for myself because I'm pretty sure after our conversation, I will have accrued more Fields medalist hours than during my time in academia. In any case, I thought we could start out by maybe you having you tell us about your trajectory in mathematics. How did you become introduced to it, and how did you decide it would become your profession?
I guess one of the main early influences was Martin Gardner's mathematical column in the Scientific American. It must have been about 10 or something when I first discovered it, where he has all these mathematical games and so on. I don't know, I guess he stopped writing it about 30 years ago, but he still has a collection of about 14 or 15 books giving his collected columns, which I can strongly recommend to anyone who's got a kid who's interested in mathematics. Since then, my career, there's just not anything interesting to say about it. It was just kind of routine, I was an undergraduate, grad student, did a PhD and some postdocs and got a job.
I see. There were no, road bumps, so to speak, any doubts or any maybe options along the way? Maybe there were different forks you could have taken, or was it pretty
not really. I was very good at mathematics and not much good at anything else. And there weren't all these distractions like cryptocurrency or whatever that all the smart people are now going into.
I see. Okay. Clearly you've had a very successful career in mathematics. That's a gross understatement. If you had to attribute your success in mathematics to any particular qualities, can you name any? Is it, I don't know, hard work, choosing the right problem that suited your strengths, or any maybe special computational abilities you might have? I don't know. Is there a list?
Luck and obstinacy. Need a certain amount of luck. Mathematics has hundreds of hard unsolved problems. I just happened to be working on one where there was something interesting to be discovered. There are lots of other areas I could have put the same amount of effort into it and got nothing. The other is just obstinacy. After failing, 57 times at something, you just keep going and trying again until something works.
Oh, that's great. Well, I'm glad you chose the right problems to be stubborn on. Why don't we go ahead and kind of get into the main meat of the conversation? Today, we'll be doing a deep dive into your work, specifically the work which I believe you are most well known for and was a significant part of your Fields Medal Award, which is the resolution of the Monstrous Moonshine conjecture. It was a conjecture formulated by John Conway, your thesis advisor, and Simon Norton. And it relates to seemingly unrelated objects in mathematics, the monster group on the one hand, and modular forms on the other hand. And the name Monstrous Moonshine refers to the fact that the claimed correspondence involving the monster group is something quite bewildering or surprising and out of the blue. Before we go into the details, Richard, maybe did you want to give us a high-level overview of the topic, your thoughts on Monstrous Moonshine, its significance, and your relationship to it?
Well, you summed it up pretty well. As I said, Conway and Norton came up with this absolutely bizarre conjecture relating the monster to modular functions. In fact, the first time I came across it was a talk by John Conway that he gave to undergraduates, where he was giving this talk to undergraduates. And I remember he hadn't actually figured out what the talk was going to be on at the start of the talk, so he had a sort of vote of the audience about what to talk on. And one of the options was sporadic simple groups, and that was the one that was voted by the audience. So he gave a talk on sporadic simple groups. And he mentioned the monster group. And at some point he mentioned that the monster had the smallest space it can live in has dimension 196,883. And he mentioned that there was this weird function called the elliptic modular function, one of whose coefficients was 196,884, just differing by one. And I remember just being completely blown away by this coincidence. It was about the most incredible thing in mathematics I'd ever seen. So somehow I guess I ended up doing research in that area largely because of this talk by Conway. So that original observation was due to John Mackay, and Conway and Norton took Mackay's idea and ran a lot further with it. I mean, this original observation could have just been a coincidence. I mean, you write down 1,000 numbers turning up in various areas of mathematics. Well, some of them are going to differ by one just by coincidence. So the first question, was this just a weird coincidence? And John Conway and Simon Norton showed that it really wasn't, because they looked at other coefficients of the elliptic modular function, and these were also closely related to representations of the monster. And more generally, they followed an idea by John Thompson to look at traces of elements of the monster instead of just dimensions of representations. And by doing that, they came up with a whole lot more modular functions. But by that time, it was really clear this wasn't just a coincidence. But at first, no one had any idea what was going on. I mean, it was relating to subjects that seemed to have nothing to do with each other, finite groups and elliptic modular functions. And their original observations were in fact first verified by Atkin-Fong-Smith, who just checked that the monster really did have representations with the properties that Conway and Norton suggested. And then Frenkel-Lepowski-Meurman explicitly constructed a candidate representation with the right properties. Really, the remaining problem was to sort of tie up these two different possible solutions. So on the one hand, Frenkel-Lepowski-Meurman had this explicit representation, which seemed to satisfy Conway and Norton's conjectures, but it hadn't been checked completely. And on the other hand, Atkin-Fong-Smith had sort of verified there was some representation for which these hold, but it wasn't clear that it was the same as the one constructed by Frenkel-Lepowski-Meurman. So I guess the remaining open problem was to sort of tie these two different solutions together.
Okay. Actually, just curiosity, you said you were inspired by this talk that John Conway gave. Were you were you a graduate student at the time?
It was an undergraduate talk.
Oh, I see. And then I guess maybe that inspired you to become John Conway's student later.
Well, sort of. I mean, it's a bit more complicated than that. In fact, I was so disorganized I hadn't actually got round to finding a supervisor, and I had no idea how to go about finding one. John Conway actually walked up to me in the library one day, and he'd sort of heard I was drifting without a supervisor, and he just asked me if I wanted to work with him. So I was sort of saved by John Conway. He actually had a good track record of doing that. He had, if students got into trouble or weren't getting anywhere, John Conway would quite often kind of rescue them. I mean, I know 2 or 3 people he did that with.
That's great. That's great. Okay, let me write out an outline of a trajectory I think we could follow, and before we get started, just to kind of give an outline of how things are going to go. We've already mentioned a few of the ingredients of Monstrous Moonshine. And of course, to state what the Monstrous Moonshine conjecture is, we're going to have to spell out all those details. So sort of maybe the first thing we should talk about is what exactly is the monster group to begin with. And I guess what we might want to talk about some, finite group theory, group theory review, just to kind of put the monster group in its proper context, so to speak. And then the second part of this correspondence in the Monstrous Moonshine conjecture is these objects called modular forms, which you've already mentioned. And then once we go into the details of what those two objects are, then we could state what the Monstrous Moonshine conjecture is. It's no longer a conjecture thanks to your work, and I guess there's also follow-up work more recently, since there are kind of other monster group objects and various associated conjectures. But yeah, I guess a large, if not all of it, has been resolved, I believe now. So we'll state the conjecture, and then the fourth part will be, well, depending on how deep we want to go, we can talk about sort of details of the proof. How does this outline sound to you, Richard?
Sounds great.
Richard, why don't you tell us more about the monster group?
Okay, sure. Well, first of all, for anyone who wants to know more details about it, the best place to do is you can just check the Wikipedia article, which actually gives a pretty good summary of it, unless someone has edited it since I last looked at it. Presumably, the audience knows that a group is basically a sort of collection of symmetries of something. And there was this big project to classify all the finite simple groups. So simple groups are ones that can't be decomposed into smaller groups in some sense. And the classification of finite simple groups is the longest and most difficult theorem in mathematics in some sense. And if it was written out in full, it would be 10,000 or 20,000 pages or something. I think there are only 2 or 3 mathematicians in the world who now have a reasonable understanding of most of the proof. And Michael Ashbacher probably knows most of it, but he's got a head start because he wrote most of it. But other than him, there are very few people who understand what's going on. Anyway, so the classification said that most of the simple groups fall into one of 18 families. So you get things like the alternating group that everyone comes across in the first course on group theory. That would be one family. And as well as these 18 families, there are 26 left over. So the smallest of these leftover ones is called the mature group M11, which is order about 7,920, if I've remembered correctly. And the largest is the monster, whose order is about, it's ridiculous, it's about 10 to the 54, so more than the number of elementary particles in the Earth. So the monster group was originally first discovered by these 2 guys called Fisher and Griess. And the problem was to show that it actually existed. We had some sort of evidence that it existed. There were all these weird coincidences going on, which would be explained by such a group. But actually proving it existed seemed out of reach. It was just too big to construct. So there are 2 standard ways of constructing groups. You can either represent them as symmetries of some finite collection of points, or you can represent them as symmetries of a vector space, like rotations. And the smallest number of points you need for the monster is again, it's sort of ridiculously large, about 10 to the 30 or something. So it's too big for computers even today to handle. And the smallest dimension of a representation is 196,883 times 196,883. And back in those days, that was in the 1970s, that was simply far too big to store on a computer. I mean, these days we think of 1 gigabyte as being nothing, but those days computers just didn't have that amount of memory. So it seemed to be impossible to construct. But Robert Griess came up with this absolutely incredible construction. He managed to do it entirely by hand without even using a computer, just by being, instead of getting a computer to do all the hard work, he was just very, very smart and came up with this incredibly complicated hand construction. I remember it came, his construction came out just when I was I think a third-year grad student, and John Conway and Simon Norton had this seminar where they were going through Robert Griess's construction of the monster, and I was completely lost after the first lecture. I mean, using all these very difficult calculations that I just had no idea about. So anyway, he managed this tour de force of actually constructing the monster, and the construction was incredibly complicated. Like, you had to construct this 196884 dimensional space, which he did by taking a sum of two rather complicated spaces, and then he had to define an algebra structure on this, which was mind-bogglingly complicated. I remember there were sort of half a dozen random constants in his definition, all of which had to be chosen just right in order to make everything work, and so on. I can't imagine how he did it. It must have taken him months or years of trial and error.
By the way, where does this number come from? This 198. So I forget the rest of the digits.
196884. Well, in Robert Griess's construction, he had to take it as the sum of two or maybe even three vector spaces, and these vector spaces were constructed in various ways. So one of them was the construction of, you tensor product a certain spin representation with some other representation of a group, and that gives you something like 2 to the 12 times 24 as the dimension of this vector space. And then there's another vector space constructed as maybe the symmetric square of something, which gives you or the alternating square, or which gives you another complicated number, and you just add up all these random looking numbers, and it just happens to come to 196883.
I mean, well, I'm still not clear about what the motivation is. I mean, you can add a bunch of things together and try to get a large number, but what's the reason for whatever this construction was in the first place at a very high level?
Because it works. There just isn't a simple reason for it. What you do is you look at it and say, well, if the monster does exist, and if this representation of dimension 196884 exists, then what does it look like if you restrict it to one of the subgroups of the monster? And one of the subgroups is this complicated group, which is a sort of, it's related to Conway's group of symmetries of the Leech lattice, only a bit more complicated. And the representations of that group are known, and you can sort of figure out, well, how does the monster representation split up as a sum of representations of this modified version of Conway's group? And you can guess how it does. And, so this Conway's group has these representations of dimension 24 and 2 to 12 and so on, which are fairly well understood, and you can sort of tensor them together and combine them in various ways.
So let's backstep a bit. So it sounds like before the monster group came onto the scene, there was Conway's group, correct?
Yeah.
Yeah. What is Conway's group?
Conway's group is more or less the group of symmetries of the Leech lattice, which is this dense sphere packing in 24 dimensions. In fact, it's been in the news recently because Marina Wierzowska found this absolutely incredible proof that the Leech lattice is the best possible packing in 24 dimensions in some sense.
I see. Okay. So before this, we have the Conway group. Okay. And it's, I don't know if it's an equals, but maybe like parentheses equal symmetries of the Leech lattice?
Up to a factor of 2.
I see. Is it like some kind of like double cover or something like this?
Yeah, exactly. The symmetries of the Leech lattice are a double cover of Conway's simple group.
Ah, okay. Got it. Okay. I see.
So if you look at the Leech lattice, you can ask, it's this sphere packing. You can ask how many spheres touch each given sphere. And the answer is 196560, which, as you notice, is suspiciously similar to 196884, the monster group.
I'm a little surprised how large this number is, because the Leech lattice is a lattice in 24 dimensions. So very naively, if I think of a lattice in 24 dimensions, right, I'm going to get a number comparable to 24 in terms of things, how many things are adjacent to
you
something.
might guess it was 24 squared or 24 cubed or something, but in fact it's more like that. There's more room. I mean, spheres in high dimensions are much smaller than you think they are. There's a lot of room for fitting spheres together.
Okay, so there's a certain sphere packing associated to this Leech lattice, such that it's the valence of a sphere in terms of how many other spheres are adjacent to it is this large number you just wrote here.
Yeah.
Oh, wow. Okay, I see. So let's continue the story. So the Conway group already gives you this large number by virtue of its correspondence with the Leech lattice. And then where does the monster group story come in?
Well, as I said, you have to, if you're trying to construct this representation of the monster, you first sort of restrict it to this a minor variation of Conway's group, and work out, if I remember correctly, that the 19688 three-dimensional vector space actually splits as a sum of maybe three representations of this cover of Conway's group. And you can work out what those are and add up their dimensions. And so you sort of know this representation when restricted to Conway's group. And the hard problem is to try and find an extra symmetry that you can add to this that generates the monster. And that was the difficult problem that Robert Griess had to solve.
The monster group was still kind of conjectured to exist at the time, right? So I'm just trying to figure out, there's several things going on here. There's sort of like, why was it even conjectured to exist? You can have the conjecture of it existing from the classification of finite simple groups and all that algebra, or you can have it arising from what I will call geometry in terms of this Leech lattice. I'm just trying to figure out the relationship between these sorts of different evidences. Do you know how those two are related?
Roughly. So the way the monster group was originally conjectured to exist was Fisher had come up with this conjectured other simple group, which is later called the baby monster, which is, again, it was huge, size about 10 to the 30 or something. Actually, maybe, I'm not really quite sure. I forgot these numbers. And the baby monster wasn't known to exist, but Fisher and Griess sort of noted that if it did exist, then it probably had a double cover. And then a lot of the sporadic simple groups have been discovered by guessing a double cover and guessing that was the centralizer of an element of order 2 in a new simple group. So in particular, there was a mathematician called Dynkin who was really good at finding new simple groups by this method. So what you did, you take this group you don't yet know exists, called the baby monster, and take its double cover that you don't know exists. And then you guess that maybe there's a new simple group with centralizer of involution, this double cover. So let's see. I'm sorry, so the baby monster, I think, would normally be called, sometimes called F2 or F2 plus or something. And it's got a double cover, which is denoted by 2 dot F2 plus. This double cover then leads you to the monster group. as I said, each of these steps is kind of conjectural. But if you guess there is a group like that, then you can guess various properties it has. For instance, you can figure out it's got a subgroup closely related to Conway's group. So there was a reasonable amount of evidence that the monster existed, but actually constructing it was a really big problem.
How do I say? In the classification of finite simple groups, there are these sporadic ones, which these monster groups fall into, and there's I think there's 27 of them, or 26, depending on how you count things, if I recall correctly.
It depends what you count as a sporadic group.
Right. How do I say? Was it the case that you had to know there were these exceptional groups, and then it was about finding them, and hence they were conjectured to exist? Or is it kind of one of those things where your classification hasn't exhausted everything, so you just kind of have to keep on looking kind of willy-nilly until your theorem is strong enough to know that you've sort of exhausted all the possibilities, so to speak?
It was very complicated. This was mostly in the 1960s and early 1970s. So there were a lot of finite group theorists who were working on finding new sporadic groups. So they'd keep looking in weird places, and occasionally, if they were really lucky, they would find one. And there were other mathematicians who were working on classifying the groups, showing that you didn't get any more. And there wasn't actually much overlap between these two groups of people. I mean, there were a few people like Suzuki who both classified groups and found new sporadic ones, but most people were either doing one or the other. So almost every one of the 26 sporadic groups was found in a different way, and quite often what would happen is one person would come along with evidence that it existed, and then someone else would come along and actually construct the group. So a lot of the groups are kind of named after two people, one of whom originally guessed it existed and the other of whom found it. And then a few years later, the people classifying groups would kind of catch up with it and show that it was a unique group with some complicated properties.
I guess I'm trying to get the sense of, like, in terms of talking about evidence of this group or that group, is it the case that you look at the current classification scheme and you're like, well, is that all? If that's not all, then I should look sort of in the most fertile space where I might find something new, right? Is that sort of?
Yeah, well, there were all sorts of different ways. I mean, Fisher found several sporadic groups by looking at groups that were generated by elements of order 2, such that the product of any two of them had order 1, 2, and 3. And he was interested in these because the symmetric groups have this property, and he found this very intriguing and tried to find all groups of that property. And John Conway found new sporadic groups by looking at symmetries of the Leech lattice, which, I mean, John Leech had discovered this lattice in 24 dimensions and went around for a few months trying to persuade other people that its symmetry group might be interesting. And there must be a lot of people who didn't take him up, who ended up kicking themselves, because if they had, they would have found this new sporadic group. And Yanko found several groups by guessing centralizers of involution and then trying to investigate if that gave you a new sporadic group. So there were all sorts of different ways that people had for finding new sporadic groups.
Actually, maybe this is a bit of too much of a tangent, but as I was reading about the classification of finite simple groups, this thing you just mentioned about looking at centralizers of involution seemed to be a key conceptual framework. What's so important about that step?
It's roughly the way the classification goes. I mean, if you want to summarize this, 20,000 pages of the classification in one line, you would say, well, if you've got a simple group, you first figure out what the centralizer of an involution has to look like, and then you try and find all groups that have that as a centralizer of an involution. So this was, I think, suggested by Brouwer and Fowler back in the 1950s, who showed there are, for a given centralizer and involution, there are only a finite number of simple groups that have that as a centralizer and involution. So this gives you a sort of way of getting hold of all the simple groups by working up from smaller ones.
So there's this theorem by these mathematicians that says there are only finitely many simple groups with this data of a centralizer and involution.
Yeah, once you fix the centralizer and involution, that almost determines the group. And the centralizer and involution is a smaller group, so you can sort of work your way up by induction on the order of the group with a lot of work.
Huh, okay. Is it too much to write the precise statement, or is that maybe that we should just leave it at that?
Well, that's precise statement is thousands of pages long.
Oh, I see.
Maybe I can try and write something down. So yeah. if you take the symmetric group Sn, which isn't quite a group but is close enough, then inside the symmetric group Sn, it's got some involutions. So it might have an involution consisting of just switching the numbers 1 and 2. So Sn is all permutations of the numbers from 1 to n. And you might switch the first two. And if you look at the centralizer of this, well, you get a group of order 2, and then you get all permutations of all the other n-2 elements. So this gives you a smaller group, which is a centralizer and involution in Sn. So you can find Sn by looking for all groups with z over 2z times Sn minus 2 with centralizer and involution. And you can see you've sort of worked your way up from Sn minus 2 to Sn by doing this.
So basically there's this kind of classification that's going on. It's incomplete. There's all these sorts of various groups being proposed. At some point it gets completed, but the Monstrous Moonshine conjecture was kind of formulated while the monster group hadn't even been shown to exist yet, right? There was just, I guess, evidence that it existed. And then the conjecture kind of said, there is this group and there is this correspondence, which we'll get to later.
Yeah. Well, I think the Monstrous Moonshine conjectures probably appeared, maybe a couple of years before Griess actually constructed the monster.
Is there anything else we should say about the monster? I feel, let's try to write something concrete. So we kind of had this very roundabout way of giving the historical approach to the monster. But I think there is a short definition, right? It's just the symmetry group of this Griess algebra.
Yes. So the Griess algebra, can't remember a standard name for it. Let's just call it V. So you've got an algebra, and Griess managed to show it's got a bilinear product on it. So there's a map from V times V to V, making it into an algebra. And this algebra is a bit of a mess since it's not associative, which makes it rather difficult to handle. So he constructed this product on V and showed that the monster was the group of symmetries of V that preserve this product. And you can sort of see why his construction was so complicated, because V was the sum of 3 pieces, A plus B plus C. So in order to define this product, you can have either A or B or C here, and either A or B or C in the second factor, and the result of this product is going to be a sum of something in A and something in B and something in C. So you can see you're getting, sort of 27 different pieces that you have to deal with in order to define this product. And you can cut that down to about 6 by using various symmetries and so on, but it still means there's an awful lot of ambiguity in what this product might be that you have to settle before you've constructed the monster.
Is there anything else we should say about this? I feel like there's still probably a lot of mystery to be plumbed out of this. Like I don't really know what A, B, and C are, for example. But
well, A, B, and C will be representations of this extension of Conway's group. As I said.
Oh, I see.
I've constructed V as the sum of 3 smaller vector spaces, and I was just pointing out that in order to find a product on the sum of 3 smaller vector spaces, it's really rather complicated.
Let's just take stock because we've been kind of all over the place for a while. So the monster group I guess it's just denoted M for our purposes.
Yeah.
Okay.
Yeah, that's a good name for it.
Okay. The monster group M is the automorphism group. Of this Griess algebra. And its order is what did you say it was, like roughly 2 to the 54, something like that?
About 10 to the 54.
Or 10 to the 54. Okay. Okay. Do we need any other properties? I guess maybe one other property that you already alluded to but didn't say explicitly was that this 198664, that is the dimension of the Griess algebra, and it's the smallest non-trivial representation of M. Is that correct?
Almost, yes. So I think Griess's algebra has dimension 196883, in fact, but it's sometimes a good idea to add a one-dimensional space to it. And there are two slightly different algebras.
Okay, but the original Griess one was 196883.
Yeah, and I think people usually add a one to it because it makes it a little bit neater.
I see. Although, okay, for the purpose of the conjecture and things like that, I guess they think of it these two numbers as being different.
Yeah, and I mean, adding one means you can do things like you can give the Griess algebra an identity element and things like that.
Okay. Okay. Is there anything else you want to say about the monster group, or should we just go on to modular forms?
We could just go on.
Okay. Why don't you tell us about modular forms and maybe kind of write down some formulas, I suppose, or draw some pictures, because it's a very rich and beautiful subject.
Yeah. The problem is when everybody first sees modular forms, the first reaction is this completely bizarre artificial definition. Why is it of the slightest use? So if you look at a definition of a modular form, it's a sort of f of a tau plus b over c tau plus d is equal to c tau plus d to the k times f of tau, which just looks sort of ridiculous. So I'll try and explain what's going on. First of all, what you've really got is the group SL2 of Z, which has all matrices A, B, C, D. And this acts nicely on the upper half plane because you can have A, B, C, D acting on tau is equal to A tau plus B over C tau plus D. So here we have the imaginary part of tau. You want that to be greater than 0 so that everything is defined. And that gives you a nice group of symmetries of the upper half plane. What you're really doing is looking for functions that are invariant. So you say f of g of tau is just f of tau, where I'm writing g for this matrix. I'm just writing G for this matrix A, B, C, D. So you just want functions that are invariant under the symmetry, and that's a reasonably nice condition.
So let's just back up for a second. So let's just make sure everyone's on the same page here. So tau is a point on the Riemann sphere, which is just the complex numbers union infinity, correct? So,
yeah.
And what you just wrote here, f of g of tau equals f of tau, that's the special case of a modular form where the weight k is 0.
This is what you get if k is equal to 0. These are called modular functions. And you usually add some other minor conditions. You want them to be holomorphic and so on, but those somehow aren't terribly important. This is the really key condition, that they're invariant under these symmetries.
By the way, just why is it called, where does the term modular come from?
It originally comes from Riemann's notion of a moduli space, I believe. So a moduli space for elliptic curves is a space that has one point for each sort of elliptic curve. So its points classify elliptic curves. And it turns out the moduli space for elliptic curves is more or less the upper half plane divided out by the action of this group SL2Z. So a modular function is really, you can think of it as being a function of elliptic curves in some sense.
Ah, I see. Modular, I see. Okay. So modular is just referring to moduli.
Yeah.
Okay, great. Okay.
The next problem is, can you give any examples of modular functions? And it turns out the simplest one is incredibly complicated. It's the so-called elliptic modular function. So it's equal to q to the minus 1 plus 744 plus 196,884q plus even worse. So it's got these, ridiculously large coefficients, and you notice immediately that this coefficient 196,884 is this number we've been talking about connected to the monster.
Mm-hmm.
You can ask, where on earth does this weird function and these funny coefficients come from? And it turns out it really comes from the following. It's equal to E4 of tau cubed divided by delta of tau. I've got these right. So these are not modular functions. They're called modular forms. So E4 is a modular form for weight k equals 4, and delta is a modular form for weight k equals 12. And so this thing is weight 12 and this thing is weight 12, and when you divide them out, all the k's sort of cancel out with each other. So next you have to ask, what on earth are these things with k equals 4 and k equals 12 and so on? Well, they're actually examples of modular forms. The modular function is invariant under SL2Z. A modular form is something like a f of tau d tau. And you want this to be invariant. So what you do is you look at f of a tau plus b over c tau plus d times d a tau plus b over c tau plus d. And you want these two to be the same. And if you work out what that means, it just means f of a tau plus b over c tau plus d is equal to c tau plus d squared f of tau. So this is where this funny factor here is coming from. It's really saying you shouldn't be looking at the function f of tau. You should be looking at the form f of tau d tau. And more generally, you can look at forms f of tau d tau to the power of k over 2 and ask for these to be invariant, and that gives you a factor of k in the exponent rather than a factor of 2.
Yeah, so I guess the way to say this in geometric language is that you have this line bundle given by holomorphic forms. That's exactly what you just wrote here. And if you want this, so the action of the modular group extends to an action on this line bundle, and if you want an element, the section, to be invariant under that action, then this f has to be a weight 2 modular form.
Yeah. If you want to give a very high-powered explanation of this transformation formula, you say it's saying that f is a section of a line bundle over the moduli space of elliptic curves. But so saying f of a tau plus b over c tau plus d is c tau plus d squared f of tau is rather easier to understand, even if
that's right.
But in some sense, that's a sort of deep explanation of why modular forms are important. They're sections of line bundles.
Mm-hmm. Okay. You were about to motivate some of the terms in the J function, correct?
Yes. So if we go back, we've got these functions E4 and delta, which are in fact modular forms. So the definitions of these look like, so E4 is 1 plus 240 times the sum over n of sigma 3 of n times q to the n, and delta is q times the product over n greater than 0 of 1 minus q to the n to the 24. As you can see from these formulas, there's a lot of theory behind these that I'm kind of suppressing. I've just written down the power series expansions of E4 and delta on the bottom right-hand corner.
Okay, so there's a kind of an equal sign here, I guess.
Yeah, exactly. Yes. So if you want to work out this number 196884 explicitly for yourself, you can just expand these two power series and divide one by the other, and you can just about do it by hand if you're patient.
Sorry, are there two equal signs? Or these are two different lines? Is that what we're? Sorry,
yeah. So delta is equal to this thing on the bottom, and E4 is equal to this.
Okay, got it. Okay, I see. So it's the ratio. It's the ratio of those two power series.
Yeah. Yes, except we've got a cube E4.
Yeah. And sorry, you have these coefficients called is that a sigma 3? There's just some functions?
The sigma 3 is the sum of the cubes of the divisors of n. It's a standard number function.
Oh, I see. It's a number theoretic function. Okay.
Yeah. So E4 is something called an Eisenstein series, and there's a whole lot of Eisenstein series. You can have E6 and E8 and so on, and they have slightly different definitions. So sigma 3 becomes sigma 5 or sigma 7 and so on. And this 240 is something to do with a Bernoulli number.
Okay. All right, lots of deep mathematics on this side. I think in my preparation for this, I think the significance of J was something like the algebra of modular forms is generated by J.
Yeah, exactly. So J of tau is the simplest modular function apart from constants, and every modular function can be written as a function of J.
Yeah, I guess a rational function of J. Let's continue.
So I guess we've discussed roughly what a modular function is. So suppressing a lot of interesting theory.
Yeah. Maybe one thing we didn't mention, just to say it, the reason you wrote things in terms of this Q equals e to the 2 by it is because one of the elements of the modular group is translation to the right by 1. So that corresponds to this element I'll just write here. I think it's 1, 1, something like that. I think that's right. Yeah.
Correct. So in particular, J of tau is periodic.
That's right. That's right.
And since it's periodic, it has a Fourier series expansion. That's more or less the same as its power series expansion in Q.
Right. So you basically have a Fourier expansion along each real line, and then it being holomorphic tells you that actually all those individual Fourier series have to stitch together into this power series in e to the 2 by I tau.
Yeah, so something like that.
Yeah. Okay. Okay, great. Okay, let's continue.
I guess I could mention a few other modular functions.
Sure.
So the elliptic modular function is the main one, but Conway and Norton used a lot of other modular functions. So the elliptic modular function uses the group SL2 of Z, which is all numbers A, B, C, D, with AD minus BC equals 1. So that should be a minus. And A, B, C, and D are all integers. So, and you can ask, what is special about the group SL2Z? And the answer is there really isn't anything special about it. So you can instead look at subgroups of SL2Z. So it's got a subgroup which is called gamma 0 of 2.
Well, I would say SL2Z is special, right? Because basically it's the set of elements that preserve lattices, essentially, right?
Yeah, but you can also talk about lattices with extra level structure or something. And this is the subgroup of SL2Z with C congruent to 0 mod 2. So it's just even. And you can ask for functions invariant under this group. And there are a whole lot of other groups. So gamma 0 of n, you can just take C as congruent to 0 modulo n. And for each of these groups, there's sometimes an analog of the elliptic modular function. So that there's a whole lot of other functions similar to the elliptic modular functions, only perhaps a little bit more complicated.
I never really studied number theory. I mean, I guess the fact that you have, modular or arithmetic conditions on the coefficients already kind of is very suggestive of number theory, but superficially at least. But what is the significance of these groups? I think they're called congruence subgroups.
Yeah. There are examples of things called congruent subgroups because the coefficients are defined by various congruences, like C is congruent to 0 mod n. Mm-hmm. And the significance of congruent subgroups is one of the really big mysteries of modular forms, because there are a lot of subgroups of SL2Z that aren't congruent subgroups. In fact, it turns out most of its subgroups are not congruent subgroups. And you can talk about modular forms for these non-congruent subgroups, and modular forms for non-congruent subgroups seem to be a mess. It's very difficult to say anything very much interesting about them. Modular forms for congruent subgroups behave really, really nicely, and nobody knows why. This is just one of these mysteries that congruent modular forms behave well and non-congruent ones don't.
I see. So you have a smaller group of symmetries, and therefore you have a larger space of functions, right? Because you have fewer constraints, right?
Yes, sure.
Okay, so where are we going to go with this?
Well, I'm just saying. So Conway and Norton needed these congruent subgroups in their description of Monstrous Moonshine. So they were sort of assigning a subgroup to each element of the monster, and the trivial element of the monster corresponds to the subgroup SL2Z, and other subgroups of the monster correspond to various other groups. For instance, gamma 0 of n corresponds to an involution related to the Conway simple group.
Sorry, for which value of n?
For n equals 2. So gamma 0 of 2 is the group corresponding to Conway's group.
I see. So there's some kind of natural dictionary between elements of the monster group and subgroups of SL2Z. That's the
almost, except some of them aren't subgroups of SL2Z. Things are a bit more complicated than that. So, for instance, there's a group gamma 0 of 2 plus, which is generated by gamma 0 of 2 and an extra element which is 0, 1, minus 2, 0. And this element here isn't actually an element in SL2Z, so it's
okay.
Some of them aren't quite subgroups. They're groups containing subgroups of SL2Z.
I see. So to be safe, maybe GL2Z then.
Yeah, SL2Q.
SL2Q.
I
see.
SL2 of the rationals. Actually, I'm not even sure. No, even that's not quite right. Let's say GL2 of the rationals.
Okay. Sorry, and this correspondence exists purely for the conjecture that Conway and Norton wanted to state, or is there some a priori reason why you have this correspondence?
There's no a priori reason that I know of why there is this correspondence, and in fact, It's still a bit of a mystery in some sense. It's not quite one-to-one. Sometimes two different elements will correspond to the same subgroup, and there are plenty of subgroups that don't correspond to anything in the monster. So it's not a bijection.
Okay, this strikes. Sorry, this strikes me as rather puzzling because we did say, I mean, of course, this correspondence is puzzling, but I'm referring to the fact that you can even define this thing because this M was this horribly large group, also very non-explicit. It's just some symmetry group. And now you're telling me you can define this map. How would you even, I mean, like you have to somehow be able to characterize the elements of M because you can't enumerate them, right?
No. Well, fortunately, it's a bit easier because if two elements of M are conjugates, so this says that G is equal to H G prime H to the minus 1, then G and G prime are called conjugate, and they both correspond to the same subgroup.
Okay, I see. So now you don't have to worry about conjugacy classes, and if I recall, it's much smaller, like 194. This number, right?
Yeah. So the number of conjugacy classes is, as I said, it's about a couple of hundred. So you can handle those by hand.
I see. Okay, so you have to know enough about the monster group to be able to classify the conjugacy classes.
Yes.
Mm-hmm. I see.
The conjugacy classes and the characters of the monster have been worked out earlier by Fisher, Livingston, and Thorne, I think.
Yeah, it's kind of funny with the history. So was it like a putative character table in the sense that we don't know if this group exists, but if the group does exist, then this has to be the character table kind of logic?
Exactly, but it was even vaguer than that because they made several guesses while calculating the character table. So it was, if the monster exists and these plausible statements also hold, then this is the character table.
And this is extremely odd because the only way I've learned how to do character tables is when I already have the group and you play around or you exploit some other theorems about group theory and you can get the character table. How do you get a character table before having the group? It just seems very backwards.
Well, they had to make some guesses. For instance, one thing they did was they guessed there was a representation of dimension 196883, which was known to be the smallest possible, and you sort of guess that there is a representation of that dimension, and that gets you started. Mm-hmm. How they went on from then, I honestly have no idea.
Okay. All right. Anyways, okay. I just remember looking at this history and just it just struck me as odd as how many tentative things you could have before finally getting the object that you actually want. Anyways, actually, we probably now have the ingredients to state the monstrous moonshine, if I'm not mistaken, right?
Yeah, sure. So how would you state this? Well, first of all, and just recall what the character of a representation is. So if M is a group, which would be the monster, and V is a vector space acted on by the monster, then it's got a character. It's just the trace of the element G acting on the vector space V. And what Conway and Norton suggested was that M acts on this huge representation, so it'd be V minus 1 plus V1 plus V2 plus V3 and so on. So it's going to be some sort of infinite dimensional sum of all these spaces. And now you can look at the trace of an element of G on this. Well, it's infinite dimensional. So to make sense of the trace, you need to kind of split it up. So we're going to look at the trace of G on V minus 1, and we're going to multiply that by Q to the minus 1, and then we're going to take the trace of G on V1 and multiply that by Q to the 1. And we sort of carry on like that. You take the trace of G on V2 and multiply that by Q squared and so on. So that's going to give you some sort of power series in Q.
Sorry, what is this decomposition you wrote here for V minus 1, etc.?
I'm just saying I've got a vector space V, which is going to be the sum of an infinite number of subspaces, and I'm just going to call V minus 1, V1, V2, and so on. It's an infinite dimensional vector space acted on by the monster.
Okay.
Conway and Norton sort of suggesting the existence of.
Oh, okay,
so
I see.
You can write down all these functions here, and what Conway and Norton said is that if G is is any element of the monster, then this function here, let's call this function f, is something called a Hauptmodul for some group gamma in GL2 of Q. So what does a Hauptmodul mean? Well, it means it's something like the elliptic modular function J, except for a more complicated group.
Okay.
Let's just write out the special case when G is 1. So we've got G is 1. Then the Hauptmodul is going to be Q to the minus 1 plus 196,884Q, and so on. And now you notice the trace of 1 on a vector space is just its dimension. So what this says is that the dimension of V minus 1 is equal to 1, and the dimension of V1 is equal to 196,884, and so on. So the dimensions of these vector spaces are just the coefficients of the elliptic modular function.
There is this vector space V, which you wrote, which was infinite dimensional. It's fixed. The things that are varying are these choices of elements, depending only on the conjugacy classes.
Yeah. So for each element of the monster, you get this complicated power series.
Yeah. Let me just write that explicitly, right? So for each, let's see, there's this conjugacy classes of M. Then you get these power series or Hauptmoduls, right?
Yeah.
I'm not sure I'm spelling it right. Is it like that?
Yeah.
Okay.
The plural of Hauptmodul is sort of debatable. It depends whether you think of it as being an English or a German word, I think.
Okay. Okay. That won't concern us for this discussion. Okay. So, please continue.
Yeah. So for instance, if you take G to be an element of type 2A, which means one of the elements of order 2 in the monster, then the corresponding group would be this group gamma 0 of 2 plus that I mentioned earlier. And here I think the corresponding Hauptmodul looks like Q to the minus 1 plus, I think it's 4372Q plus. I'm not guaranteeing I've remembered all these numbers correctly. So what this would say is the trace of this element G on V1 is 4372, and so on. So you can do something similar for every other element in the monster and every other one of these vector spaces Vn.
So there's V, and each of these VIs is irreducible?
No, not at all.
Okay. Of course not. Yeah, I mean, there's the trip. Okay, sorry. Yeah.
All of them except V minus 1 are reducible.
Okay. The way they're grouped is just to give the coefficients of the Qs.
Yeah. Yes.
I see. Right. And then I see. So these traces are actually sums of characters, not individual characters.
Yes. They're characters of non-irreducible representation.
That's right. Yeah. That's right. Yeah. Sums of irreducible characters. Yeah. Okay. Please continue.
Well, I guess that's it, and that was Conway and Norton's Monstrous Moonshine conjectures. They said there seems to be this infinite dimensional representation of the monster with this weird connection to modular functions. So I guess a clear statement would just be, we'd say if G is an element of the monster, and we look at sum over n of trace of G on Vn and multiply it by Q to the n, we say this is a Hauptmodul for some group.
Okay. I think you didn't define what a Hauptmodul is, but in my prep, I
No,
sort of
no.
came across the term. Yeah.
I thought I vaguely said it was something like the elliptic modular function, only a little more complicated. So
Yeah.
the Conway and Nod's paper gives an explicit list of all these 194 Hauptmoduls.
This is the monstrous moonshine conjecture, right? So monstrous because there's the monster group, moonshine because it makes this extraordinary claim about two unrelated things, the monster group and its representations, and then statements about modular forms. So the content of this theorem is that this power series that you wrote has the right symmetry properties, right? Okay. Mm-hmm. And historically, the way this was conjectured was just kind of in a piecemeal way, where for G equals to 1, right, there was this observation about dimensionality that you saw as an undergraduate, right? So that was the first flavor of this, and then more poking kind of gave you more terms, and then more poking said, okay, why not generalize from G equals to 1 to other elements?
Yes, I think the generalization from G equals 1 to other elements was suggested by John Thompson originally.
Okay.
That's
but then
the details.
I see. But then eventually all that merged into this monstrous moonshine conjecture.
Yeah.
Mm-hmm. Okay, so we stated the conjecture, and let's see, what year was this conjecture formulated?
Probably about 1978 or 79.
I see. And then when were you a student of Conway?
I must have started being a student in about maybe a year or two later.
Okay. So this was a very fresh conjecture. Was it a hot topic of a conjecture, or were there a lot of people working on it? Were you?
No, it was. I mean, it was a bit of a backwater. I mean, part of the problem was there seemed to be no way to. I mean, it was just relating these two things that had nothing to do with each other. So it was not clear how one could even get started on it. And in fact, I should say this monstrous moonshine conjecture was actually proved very soon after by I think it was Atkin-Fong-Smith, if I've remembered correctly. I may have got the names a bit wrong because it's a long time since I was thinking about this. So in fact, it's not, in principle, it's not really all that hard to prove, because you can prove something as a character of the monster just by checking some congruence conditions. So all you've got to do is to check a lot of congruence conditions between modular functions, and that's, it's a long computation, but in principle, it's not that difficult.
Sorry, what did these three authors prove?
That they proved the existence of this representation just by checking congruences between modular functions. You've got to check several hundred congruences, so it takes a bit of work.
I see. They proved the existence of this V representation that we talked about earlier.
Yes.
I see. Okay. So when the monstrous moonshine conjecture was stated in 1978, part of that conjecture was even the existence of V. So that's already one like kind of prerequisite of the conjecture. They proved that part.
No, they proved the whole lot. They proved it existed and had these properties that the traces are Hauptmoduls.
Oh wait, I'm sorry, but you proved the monstrous moonshine conjecture, right? So what did they prove?
It depends what you mean by the monstrous moonshine conjecture. The original conjecture was proved by Atkin-Fong-Smith.
Okay.
Almost nobody seems to have heard of this.
Sorry. So what did they prove, and then what did you prove?
Well, you can go on a bit. So the problem with this proof is it doesn't really construct the representation in a very satisfactory manner. It just says, well, you construct this representation by adding up irreducible representations, and it's doesn't give you a clear picture of what V really looks like.
So just to be clear, they actually prove this Monstrous Moonshine conjecture as you wrote it here.
Yeah, oh, yes.
I see. Okay.
Then Frenkel-Lepowski and Meurman. I can't remember how the ends Meurman has on the end. Actually constructed a space V using vertex operators. So they constructed this space V, which is sum of Vn. And so again, the dimension of Vn was equal to the coefficient of the elliptic modular function. And this was much better because instead of constructing V in this rather weird way, just summing irreducible representations, they actually had an explicit natural construction of a space V. And they could check that the so the question is, does the representation they've constructed satisfy the Monstrous Moonshine conjectures? So in some sense, we've got two different representations. We've got the representation constructed by Frenkel-Lepowski-Meurman in a natural way that has vertex operators acting on it. And we've also got the representation constructed by Atkin-Fong-Smith that satisfies the Hauptmodule property. And what you want to know is, are these two representations the same as each other?
I see. Okay. And sorry, and V was constructed by, you said vertex. What was the ingredient?
They construct using vertex operators. So this is the vertex operator.
Okay, I was hesitating because there's the notion of a vertex operator algebra, and I wasn't sure if those were the same things.
They're related, obviously.
Okay. This construction by Frenkel and the other authors, this is a representation of the monster group involving these vertex operators. Was it shown to satisfy the Monstrous Moonshine conjecture?
Frenkel-Lepowski-Meurman showed it satisfied about half the Monstrous Moonshine conjecture. So if you look at the function sum of trace of G on Vn times q to the n, you want to know if this is a Hauptmodule. And they were able to check this if G commutes with an element of order 2. So if GH equals HG for, where H is an element of type 2b, if I remember correctly. And that's because the way they constructed this, it started off with an element of type 2b. So they could sort of check that it's about half equal to the Atkin-Fong-Smith representation in some sense. But it was very difficult to get hold of elements of the monster that don't commute with an element of type 2b. I mean, so what happened is the Frenkel-Lepowski-Meurman constructed V as the sum of two subspaces, V plus and V minus. And V plus, this element of H of type 2b acts as +1, and here H acts as -1. And if an element commutes with H, then it acts on V plus and V minus, and it's easy to get hold of, and you can check what its trace is. But if it doesn't commute with H, then it mixes up V plus and V minus in a very complicated way, and it's difficult to see what it's doing. So there was sort of overwhelming evidence that these two representations are really the same, but the problem is to actually prove it.
Okay. And is that what you ended up proving?
Yeah. The bit I did was the bit at the end where you finish off the, Frenkel-Lepowski-Meurman did about half the elements, and the problem was to just clean up the remaining half of the elements and show that they also had this property.
And is this the content of your Inventiones paper?
Yes. So dealing with these remaining elements was what the Inventiones paper was about. I
see. Okay. Would it be possible to say a little bit about the details of that? I noticed there were, so there's Just throwing out some words there here. You used a no-ghost theorem motivated from string theory. There seem to be a lot of kind of things coming in.
So doing the elements that commute with an element of type 2b, as I said, is reasonably straightforward. It's just you just have to calculate traces on two known spaces. For the remaining elements, the proof is much more indirect and long and roundabout. So I guess I could give a brief summary. So first of all, V has an extra algebraic structure. It's something called a vertex algebra. Which is a very complicated algebraic structure. So most algebras have just one product and they satisfy some identity. So a Lie algebra is one Lie bracket and satisfies the Jacobi identity. The vertex algebra, it has an infinite number of products. And these satisfy an infinite number of rather complicated identities that I'm not going to write down because I've forgotten what they are.
Can you say a little bit about, like the geometry? Is it right there? I'm sure there's some underlying object that motivates. This is a formalization of some naturally occurring object in some sense.
It's a formalization of vertex operators. So what's going on is that if you've got any element V in V, then there's a vertex operator acting on V. And a vertex operator is really an infinite power series whose coefficients are operators. So for every element of V, there are an infinite number of operators on V, and this is giving you a sort of infinite number of different sorts of products. And a vertex algebra is just a formalization of the properties these vertex operators have.
If I recall, these are definitions motivated from conformal field theory?
No, they were. I didn't actually know what conformal field theory was at the time I was writing down these definitions. It actually originally, the motivation came from vertex operators in string theory.
Okay.
All the claims you see that vertex operators came from conformal field theory are just wrong. They came from string theory.
I see. Can you say, there's a lot of ways to kind of poetically describe string theory. They're just vibrating strings and you have these world sheets because strings collide and split off. Can you give a similar poetic description of how vertex operators appear in string theory?
They sort of describe what happens at a vertex of a Feynman diagram very, very roughly. That's where the name comes from. Vertex means vertex of Feynman diagram.
I see. And these are your usual Feynman diagrams of point particles?
More or less.
Huh.
Well, I mean, the product is just what happens is for each integer n, for each u and v in V, and for each integer n in the integers, you can form an element u sub n of V, which is also in V. So there's a sort of product combining u and v for each integer n.
I see. They're all bilinear products.
Yes, they're all bilinear, and you can think of them as being, you can put them all together into a power series if you like, and that power series is the vertex operator.
I see. Okay.
It's not a power series; it's actually a Laurent series, formal Laurent series.
I see. So we have this vertex algebra structure. It already pre-existed from string theory. Is that right?
What we mean?
Oh, I mean, you didn't make this definition. Somebody else made this definition.
No, I made this definition.
Oh, okay. That's what I thought, but then you said it came from. Okay, I was a little okay.
So vertex operators came from string theory. Vertex algebras was something new.
I see. You introduced this definition in your paper. There's vertex operators. The previous authors, Frenkel and others, used vertex operators, but they didn't use this vertex algebra.
They incorporated it later.
Okay. I mean, I guess there's different people have different motivations. Let me ask you: did you know any string theory or get inspiration from string theory yourself, or did you get some mathematical distillation from it?
I knew a few. I picked up a few small bits of it from Peter Goddard and Igor Frenkel. And I think Peter Goddard had some notes on Igor Frenkel's work that I had a copy of, and explained what a vertex operator was.
Okay. You looked at that definition and then at some point was inspired to define vertex algebras based on what a vertex operator was?
Yes.
Okay, let's continue. So there's a notion of a vertex algebra.
So the Frenkel-Lepowski-Meurman's representation is really a vertex algebra. So we've got these two representations, one of which is a vertex algebra, but not known to satisfy the Moonshine conjectures, and the other by Atkin-Fong-Smith is known to satisfy the Moonshine conjectures, but not known to be a vertex algebra. And what you want to do is combine these so they're the same. So it's both a vertex algebra and satisfies the Moonshine conjectures. And I guess what you do that is step 2. You go from the vertex algebra, and from it you construct a Lie algebra. This is called the vertex algebra is called the monster vertex algebra, of course, and the corresponding Lie algebra is called the monster Lie algebra. And this step here makes some rather serious use of string theory. So I'd say that this step here uses the no-ghost theorem. So this is the no-ghost theorem due to Goddard and Thorne.
Okay, so you how do I say? How did you, so these are physicists. How did you come across this result?
I came across this result because Frenkel actually introduced it. So I should say Frenkel had this amazing idea of applying the no-ghost theorem in order to prove results in mathematics. So I learned this from Igor Frenkel.
I see. What is the no-ghost theorem, roughly?
Roughly speaking, it says that if you're in dimension 26, then the space of physical states is positive definite. Actually, it would actually be dimension at most 26, but dimension 26 is the interesting one. So in string theory, you can write down a space of physical states, which should be a Hilbert space. And that means it should have a positive definite Hilbert inner product on it. And the trouble is, if you're in dimension above 26, this inner product is indefinite. It's got vectors of negative norm, which really messes up quantum mechanics. So if you want quantum mechanics to work, you must have no... The states of negative norm are sometimes called ghosts. So you want a no-ghost theorem, which says there are no states of negative norm. I think the name is also a bit of a pun on the term no-go theorem, which was common in physics.
Mm-hmm. Can you say what is the mathematic? Can you distill what you just said into mathematics? So what you construct this Hilbert space. You want to show that there are, or I guess a pre-Hilbert space, because the Hilbert space should have a positive definite inner product. But okay, you construct this vector space. You want it to be a Hilbert space. It might have some negative definite states. What is the mathematical? What is the okay? That's what you want. But what is the actual mathematical input and method of proof? What are the ingredients?
Well, the ingredients of the proof are mostly representations of something called the Virasoro algebra, which is more or less, you can think of it as being something like the Lie algebra of smooth maps from a circle to itself. I mean, it's a little bit more complicated than that because there's a sort of central extension involved. So this algebra was actually first introduced by Cartan in the early 20th century. And then sometime in the 1960s, I think, Gelfand and Fuchs and Bloch, I think, noticed it had an interesting central extension, which gave you the Virasoro algebra. And then a few years later, Virasoro came along and didn't discover the Virasoro algebra. What he discovered was the original algebra that Cartan had found in the early 20th century. So anyway, so it was actually discovered by lots of other people other than Virasoro, but things are never named after the person who first discovered it. So it's now the Virasoro algebra.
I see. Okay, sorry. So, right, the Virasoro algebra is a central extension of a certain algebra. Cartan discovered the one without the central extension. Is that what you said?
So Cartan and Virasoro found the one without the central extension.
I see. Okay. Okay. So you're saying this no-ghost theorem is a statement about a representation theoretic statement about the Virasoro algebra.
Yes.
I see. Certain representations come with an inner product. A priori, they're not definite, but there is this result that it ends up being definite in this particular dimension.
Yes. So it says if the dimension is at most 26, then the Hilbert space of string theory is indeed a Hilbert space. That's why string theory sort of works in 26 dimensions, but doesn't really work so well in other dimensions. And superstring theory is similar, except the number d gets changed to 10 dimensions. So superstring theory works really well in 10 dimensions. And this is kind of a notorious problem because we don't live in a 10 or 26 dimensional space, but whatever.
Okay.
I mean, it's a bit unfortunate for physicists, but it's really great for mathematicians because d equals 26 is exactly what you need for dealing with moonshine.
Why is that?
Well, it's because 26 is equal to 2 plus 24, and 24 is the dimension in which the Leech lattice exists.
Okay.
And this turns out to make everything fit together really neatly. So it's not a coincidence that the 26 of string theory is 2 plus the dimension of the Leech lattice. This is sort of crucial in moonshine.
I see. Is there a significance of that 2? Like what if it were 1 or 3?
The 2 is it's in the proof of the no-ghost theorem, you essentially have to start with some space in related to 24 dimensions and add on something related to 2-dimensional space-time. The Goddard and Thorne's proof very much uses 2-dimensional space-time in order to prove the positive definiteness. So you sort of need to tack on a 2-dimensional space-time to anything if you want to prove an analog of the no-ghost theorem.
Let's back up here. So you wrote down vertex algebra to Lie algebra. You needed this no-ghost theorem.
Very roughly, the no-ghost theorem allows you to go from a vertex algebra to a Lie algebra. More precisely, what you do is you take the vertex algebra and then you tensor it with a sort of vertex algebra of a 2-dimensional lattice. I mean, this is dimension 2, which is sort of related to this 2 down here that you have to add to get to 26. So this is a construction you can do with any vertex algebra. You tensor it with the vertex algebra of a 2-dimensional lattice, and then you can get a Lie algebra from that.
Because this no-ghost theorem is true.
And the no-ghost theorem means this Lie algebra is almost positive definite.
Where does positive definiteness come in?
This Lie algebra looks, at the first sight, looks horrendously complicated, and you want to know what its structure is. In fact, I can draw a picture of it. So the Lie algebra you get in the monster case looks like this. First of all, it's C squared graded. So for every pair of integers mn, there's a piece of it. So I'm going to plot the points mn in the plane, and on each point I'm going to draw the dimension of the corresponding piece. So first of all, there's a 2-dimensional piece. It's called the Cartan subalgebra. And then there are two pieces of dimension 1 and 1 that live there and then. And then there's a piece of dimension C1 there, where C1 is this number 196884. And I'm not going to write it out explicitly because it's on this diagram because it would take up too much room. And then there's a piece of dimension C2 and C3 and C4 here. And then you sort of go on like this. There's a piece of C, and then you now have pieces of dimension C2n here, and then pieces of dimension 3n.
Mm-hmm.
And these numbers Cn are cubes. So, for instance, C2 is 214936760, and they continue increasing really rapidly. They're just the coefficients of J. So J of tau is sum of Cn q to the n. And I guess it also goes down here. And so on. So what's happening is the Lie algebra is sort of zero in these two quadrants, apart from these two one-dimensional pieces. But in the top right and the bottom left-hand quadrant, the algebra goes completely, absolutely wild. I mean, it's exponentially increasing in size as you go further out. So normally when you study Lie algebras, you want them to be finite dimensional so you can handle them, or maybe if they have polynomial growth, you can do something with them. But these don't have polynomial growth; they have exponential growth. So they're far bigger than most of the Lie algebras that people consider. And the trouble is, this Lie algebra is huge. How do you control it? It looks completely wild. And the way you control it is you need to use the fact that all of these spaces are positive definite, except for this space here. So this two-dimensional space is not positive definite. But all the other spaces are positive definite. So that's why you say this algebra is almost positive definite. It's positive definite except on this two-dimensional bit where it's sum of a one-dimensional piece of norm greater than zero and a one-dimensional piece of norm less than zero.
You have control over this Lie algebra, then what?
So the no-goes theorem tells you the dimensions of these pieces. So it tells you they have dimensions C1, C2, and so on. And it tells you that you've got this positive definite form, well, except on this piece here.
Mm-hmm, mm-hmm.
And the next thing you've got to do is to work out what the structure of this Lie algebra actually is. You want to identify it up to isomorphism. And to do that, you need to use the theory of Kac-Moody algebras. If you want to picture a Lie algebra, you want to draw a picture of it. So here are some pictures of Lie algebra. Suppose I take SL2 of R. Picture it's going to be really simple. I'm just going to draw a single point. So a point means SL2 of R. And if you look at SL3 over the reals, picture that is going to be 2 points. And that's because if you look at SL3, well, you see it's got a copy of SL2 on the top left, and it's got another copy of SL2 down here. So there are two copies of SL2, and each of these gives you a point. And these copies of SL2 are overlapping, and you indicate that by drawing a line between them. And if you look at SL4, well, it's got a copy of SL2 here, and another copy here, and another copy here, and these generate it. So I'm now going to draw 3 points, because there are 3 copies of SL2, and the top left and the two ones on the top left and the middle overlap, and the ones on the middle and the bottom right overlap, so you draw lines. But the one on the top left and the bottom right are kind of not overlapping, so you don't draw a line between them. So you can draw pictures of Lie algebras by drawing a dot for an SL2 and drawing a line between some dots to indicate how they interact.
Right.
This is, of course, called the Dynkin diagram. And what Katz and Moody noticed is that you can take any diagram you like, let's just draw some dots and join them together in some weird way. And this gives you a Lie algebra called a Kac-Moody algebra. So it's by Katz and Moody.
Right. So how do I say? There's something called the Cartan matrix lurking in the background, which encodes these relations.
Yeah, the Dynkin diagram is equivalent to the Cartan matrix.
Now, I was looking at the definition of a Kac-Moody algebra, and it's basically you get a Kac-Moody algebra by relaxing the definition of a Cartan matrix for the case of the finite dimensional semi-simple Lie algebra, say to enable more general matrices.
Yeah.
The question I'm trying to ask is that relaxation equivalent to just drawing any of these diagrams you said, or there's probably some restrictions on what you can draw as well, right?
It's more or less equivalent to just drawing any diagram you like. I mean, up to technical details, which I don't think we really need to go into. So, yes, so what Katz and Moody said, you can draw any graph you like, and you can get a Lie algebra. You just take a copy of SL2 for each point and add some relations saying these copies overlap if there's a line between them.
I see.
And
That's
Moody algebra.
Okay.
And they're very similar to finite dimensional Lie algebras, except they're not finite dimensional.
I see. Although from this discussion, it's not clear why they would be infinite dimensional, because you sort of drew everything as a matrix algebra, which of course are finite dimensional.
Well, they're infinite dimensional, because if they were finite dimensional, they'd be the ones that are already known. I mean,
sure.
There's a standard list of finite dimensional simple Lie algebras. Anything that's infinite dimensional.
I see. So going from the diagram to the algebra is no longer going to be this nice matrix algebra correspondence.
You can't write it down as matrices anymore, but you can write it down as generators and relations.
Right. Yeah. Okay, great.
Yeah, it's difficult finding explicit representations of infinite dimensional Kac-Moody algebras, except for the affine ones.
Okay.
The ones that nearly everybody describes are just the affine ones, which have polynomial growth and are well behaved. But if you write down a random graph, it's almost certainly going to have exponential growth.
Okay. So the Lie algebra, this monster Lie algebra, is a Kac-Moody algebra. Is that right? That's where we're going?
No.
Oh, okay.
It's not quite, because Kac-Moody algebras have the property that all simple roots are real. So what are the simple roots? Well, these are the things corresponding to the vertices of the graph. I wrote down. So for every graph, there's something called a simple root. You can think of a simple root as being more or less a vertex of a graph. And the Kac-Moody algebras, these are real, which means that roughly that the corresponding norm is positive. So the simple roots can be real. Other roots are allowed to be not real. So in the finite dimensional algebra, all the roots are real. Kac-Moody algebras, the simple roots are real, but you allow other roots to be not real. But it turns out you can modify the definition of Kac-Moody algebra a bit. You get these things called generalized Kac-Moody algebras, where the simple roots need not be real. And what this means is that so the Kac-Moody algebras are built out of copies of SL2R, acting and finite dimensional representations of them. And it turns out that if you allow simple roots not real, then and then you have to build these out of three sorts of algebra. You can either have SL2R with finite dimensional representations, or you can have something called the Heisenberg algebra, or you can have something called SL2 of R, but you allow things called discrete series representations. But otherwise, it's much like Kac-Moody algebra. So you write down a graph, you can write down any old graph, but now instead of just drawing lines between them, you have to mark some of these roots are real, and some of them are not real. So you might sort of mark some of these roots as being real or something like that. So you can get a Kac-Moody algebra from any graph, and you can get a generalized Kac-Moody algebra from a graph, but you have to mark some of the vertices as being behaving a bit differently. And that turns out that you can take Katz's book on Kac-Moody algebras and go through it, and you find that almost everything works fine for these slightly more general sorts of algebra.
Should I think? How do I say it? What I'm trying to intuit from this is there some kind of analog of compact versus non-compact here, right? Because if you have a compact semi-simple Lie group, then if I recall right, then the killing form is going to be positive definite, right? And then if it's non-compact, then it's going to be indefinite. Is there something analogy here?
It's sort of related. Is
that the wrong way to think of it? I don't know.
Well, unfortunately, it's rather confusing because the terminology has got completely messed up, because people doing Kac-Moody algebras and people doing finite dimensional algebras use the terms real and imaginary root in quite different senses. So the terminology has got into a bit of a mess.
Okay. Okay. Anyways, I was just curious about that. Anyways.
It's sort of it's sort of related, except that the generalized Kac-Moody algebras that appear in Moonshine are sort of all analogues of compact finite dimensional Lie algebras, except they're not actually compact. They sort of have many of the properties of the compact Lie algebras. Not like that, that, as you were saying, the compact Lie algebras in finite dimensions have this property that the form on them is positive definite. And the generalized Kac-Moody algebras you work with have the property that the form is very nearly positive definite, except on a very tiny bit of it. So they're pretty close to being compact. Okay.
All right. Let's forge on. So this monster Lie algebra is a generalized Kac-Moody algebra. What's next?
Well, the next thing is, if it's a generalized Kac-Moody algebra, you want to know what the simple roots actually are. In other words, you want to know what is the graph corresponding to it. And if we go back, the easiest thing to do is to go back to one of the earlier slides. So if I go back to slide 15, now indicate the simple roots. And the simple roots are just these things here. So these are the simple roots.
Okay.
They're just the things lying in the first column beyond the origin. And so this gives you a complete description of the algebra, because if you know what the simple roots are, then that sort of tells you everything. You can ask, why are these the simple roots? Well, it turns out to be related to the following identity. So if you take J of sigma minus J of tau, and this is a very nice product expansion. It's product over M, 1 minus P to the M, Q to the N. So it's CMN. So there should be a Q to the minus 1 there, I guess.
And what is sigma?
So Q is equal to e to the 2 pi I tau, and P is equal to e to the 2 pi I sigma. So we've got two variables, sigma and tau, which are both in the upper half plane.
Okay.
Um,
Okay.
and so this identity, its history is a bit obscure. It seems to have been found by Simon Norton, and then it was proved by Koike, except they didn't write it as an infinite product. They wrote it out as a complicated series of recursion relations for these coefficients C. And Zagier probably knew about it as well. But rather oddly, none of these three ever published it. So it's kind of floating around as this unpublished identity for a few years. And it turns out to be equivalent to saying what the simple. So this determines the simple roots of the Monster-Lie algebra. And you can think of this identity, it's something like the Weil denominator formula. So if you've got a finite dimensional Lie algebra, you know there's a Weil character formula giving the character of its irreducible representation. And in particular, you can write down a character formula for the trivial one-dimensional representation, and this gives you something called the Weil denominator formula. And the Weil denominator for the Monster-Lie algebra is just this. So maybe I should give some examples.
Yeah.
So let's go
remind me what the Weil character formula is. It's been a while.
So the Weil character formula is just the van der Monde identity.
Mm-hmm.
So the van der Monde identity says that if you've got this matrix here, suppose I take a matrix 1, 1, 1, and so on, and then I take x, y, z, and x squared, y squared, z squared, and so on, up to x to the n minus 1, so on. So if I take this big matrix and take its determinant, this is the product over x minus, sorry, let me try again. It's the product x minus y, x minus z, y minus c, and so on. So you just take a product of all differences.
Mm-hmm.
And you can write this as a determinant is just the sum over sigma in the symmetric group of something. You can just expand a determinant as a sum over all things where you select one element from each row and each column. And this is just a product over I less than j of psi minus xj.
Mm-hmm.
And so the van der Monde identity just says that some sum over the symmetric group is equal to a product over all these pairs. And this is just the Weil denominator formula for the special linear group on n elements over the reals.
Mm.
So this Sn is called the Weil group.
Mm-hmm.
And this product is over something called the positive roots. So the van der Monde identity is the simplest case of the Weil denominator formula. And for other Lie algebras, there's something similar, except the symmetric group gets replaced by a more complicated Weil group, and the positive roots get replaced by the positive roots of your Lie algebra, and so on.
Oh, all right, beautiful. I didn't know about this this correspondence.
Yeah. So if we go back to slide 18, you can see here we've got a sum. So this bit here is really a sum over the Weil group.
Mm.
Well, it's a sum over two elements, and the Weil group for the Monster-Lie algebra is just z over 2z. And this is actually a product over the positive roots. So here we've got the Weil denominator formula. Sum over the Weil group is a product over the positive roots. The only thing is, you notice the sum over the Weil group, you're summing over something rather complicated. You're summing over the elliptic modular function instead of just something simple monomial. And that's caused because the Monster-Lie algebra also has some imaginary roots, and they cause some changes to the Weil denominator formula. But it's essentially the van der Monde identity and the product formula for the Monster Lie algebra are really both the same thing in principle. They're both the Weyl denominator formula for different Lie algebras.
Okay, I think we're starting to get close, right? Because the right-hand side, when you say it's about positive roots, that's a representation theoretic object, therefore. The left-hand side, if you ignore this thing about the Weyl group, that's giving you modular forms, right?
Yes. So from the Monster Lie algebra, the left-hand side will be a couple of modular forms.
Sorry, I'm still seeing. Sorry, the Weyl group on the left-hand side. You're saying it's what is it? Z mod 2Z? Is that what you wrote?
But for the Monster Lie algebra, the Weyl group only is order 2. So it's very small.
That's a very small game. I see.
That's because it only has one real root.
Okay.
Masses and masses of imaginary roots, which are giving you the elliptic modular function. In fact, if you go back, here I've written down all the simple roots. The one down here is the single real simple root. And all these numbers C1, C2, and C3, they're the imaginary roots. And as you see, they come with multiplicities given by the coefficients of the elliptic modular function.
There was a punchline. I missed it. So sorry. So we wrote down the Weyl denominator formula for the monster group.
Yes.
And is there still another step or two?
Well, pretty much almost finished, because that tells you the structure of the Monster Lie algebra. And from that, it's quite easy to identify the Conway-Norton functions.
Are you saying that there is a general Weyl denominator formula for a Lie algebra, and if you just write that down, this is what you get?
This is what you get for the Monster Lie algebra.
Yeah, that's right. Not knowing what that formula is, I guess. How did J come about? Because J.
The elliptic modular function turns up because if you look at the imaginary simple roots, they've got all these numbers C1, C2, and C3 attached to them, and these are coefficients of the elliptic modular function.
Oh, I see. I think you just said that. I see. Okay.
That's where J comes from.
Got it. Okay, because obviously the Weyl denominator form has nothing to do with modular forms, so that's how.
In general, it's nothing to do with modular forms.
That's right.
The Monster Lie algebra, you just calculate this left-hand side, and it just happens to involve the elliptic modular function.
Although, okay, I feel like the buck can be pushed back one further, because it's the Monster Lie algebra that itself had these components that had the dimensions of J, right? So there was where modular forms was already introduced, or not modular form, but like the ingredients were already there in some sense.
Yes, sort of.
Yeah. Okay. Is there a simple explanation for why this Monster Lie algebra should have components that have those dimensions of J? I mean, J already occurred. J already got somehow smuggled in to the Monster Lie algebra before you wrote down the right. Some sense.
Yeah, well, J originally appeared because its coefficients turn up in the dimension of the monster vertex algebra that Frenkel-Lepowski-Meurman constructed. So it says that they actually calculate the dimension of these components, and they were coefficients of the elliptic modular function. And then that propagates through to the Monster Lie algebra, because the no-ghost theorem shows that the dimension of pieces of the Monster Lie algebra are the same as the dimension of pieces of the monster vertex algebra.
So how did now we pushed it back. I'm just trying to figure out the real kind of entry point, so to speak, of where modular form showed up. So it already occurred in this vertex operator setting of Frenkel. How did modular forms get smuggled in there?
Well, there, if you look at the vertex algebra, a first approximation to it is to take a sort of tensor product of two vector spaces, one of which is a group ring of a Leech lattice, and the other of which is a certain Fock space. And the dimension of each of these pieces give you certain modular forms. So the group ring of the lattice basically gives you a theta function, which is a sort of modular form, and the Fock space gives you a power of something involving Dedekind's eta function, which is another modular form. So modular forms just turn up because of the way the vertex algebra of a lattice is constructed.
Okay. All right. I'll take that as an answer. Sorry. So I think you said that maybe we're one or two steps away, or just some very simple corollary now of what we have here on slide 18, this file denominator formula.
Yeah. So once you've got the structure of the Monster-Lie algebra, well, all you do is the monster acts on the Monster-Lie algebra, and for each element of the monster G, you can get an analog of the Weyl character formula, of the Weyl denominator formula. So what this says is that, let's call it f of sigma minus f of tau is a product over something or other. I don't really care very much what it was, where f of tau is just the sum of the trace of G on V to the n times Q to the n. So these things here are just the functions that Conway and Norton associate to elements of the monster. And this gives you lots of identities between the coefficients. And it turns out you get enough identities to actually determine the functions f of tau. What I mean, it's a bit of a mess, but in principle, it's not too difficult. If you expand out this infinite product, and compare coefficients of both sides, you get lots of identities between these coefficients, and you get so many identities between coefficients that allows you to determine these functions f of tau, and then you just check they are in fact modular functions.
I see. Sorry, the thing that was needed to be shown is that this f of t is a Hauptmodul, and so you okay.
Yeah, so this last step is kind of messy but routine.
Got it. Okay, I believe that. Okay. So I guess we're done. Is that right?
Yeah, sort of.
Is this the result that you're most proud of?
Well, I don't know. I mean, I don't really sort out results by how proud of them I am. I must admit that my feeling has always been the Monster-Lie algebra is not really all that interesting as a Lie algebra. I mean, it's file group as order 2. That's tiny, and means that it's, in some sense, it's pretty close to being just a free Lie algebra, or some of two free Lie algebras or something. There's a much more interesting Lie algebra, which is called the fake Monster-Lie algebra, which actually came first. That's actually a sort of twisted form of the Monster-Lie algebra, and it's got a much more interesting denominator formula. So I'd say I find the fake Monster-Lie algebra a lot more interesting than the Monster-Lie algebra.
In terms of scientific results, right? There are things that you're most famous for. There are things that you could be most proud of. There are things which are the most difficult things, and those there's a Venn diagram. They are not all coincident, right?
Yeah.
Okay, maybe you said there are other things that are more interesting. Was this somehow harder than other things you've encountered? Was there something particularly difficult about this particular proof, would you say?
Well, the main difficulty is it's not so much technically hard as it's just really weird. That some of the steps in it, like constructing a Lie algebra from the monster vertex algebra, are just it was just something no one had ever done anything like it before. So it was difficult thinking of doing that, but it's not actually a very difficult construction once you've thought of it.
I see. Would you say that was if you had to name one or two kind of major breakthroughs in this proof, would you say that constructing the monster Lie algebra would be one of those breakthroughs?
Yeah, I mean, I'd say that the monster Lie algebra is the central object of the proof. I mean, first half of the proof is constructing a monster Lie algebra, and the second half of the proof is going from the monster Lie algebra to showing that you get Hauptmoduls. So it's it's the main part of it. But yeah, I mean things like the denominator formula for the monster Lie algebra is much easier to prove than the denominator formula for the fake monster Lie algebra, for example.
To wrap this up, so there's a slightly larger story, I guess, because the monster group is one of the sporadic groups, and I think there's a monstrous moonshine for the other groups too. Correct?
Oh yes. So that was recently completed a few years ago, but by Scott Carnahan, who managed to generalize this argument to all the other groups. The big obstruction there is the vertex algebras you have to deal with are much more complicated. That somehow the vertex algebra for the monster is actually the easiest of the vertex algebras to deal with. For the other ones, for smaller sporadic groups, the vertex algebras get more complicated, which is a bit paradoxical. In particular, there's a very hard problem of constructing things called orbifolds of vertex algebras. What are the representations of an orbifold of a vertex algebra? And what Scott did was he basically combined. He was able to describe the orbifolds of these vertex algebras in sufficiently well that you could push through an analog of this proof. So for every other element you could construct. So for many other groups, you could construct an analog of the monster Lie algebra with a more complicated denominator identity.
So for someone not working in this field, are there connections to other areas of mathematics that you're aware of that might be of interest to people?
Well, there's been a lot of speculation, but much of it hasn't really. Much of it is still at the level of conjecture. I mean, Witten had this paper relating moonshine to black holes. As far as I know, this is still very speculative. There's a lot of interesting stuff recently related to umbral moonshine, where subgroups of M24 and the Nemi lattices seem to be related to mock modular forms. So mock modular forms are these things that were introduced by Ramanujan about a century ago. And for decades, no one could figure out what the heck they were. The definition of a mock modular form was basically, it's defined to be one of these functions written down by Ramanujan. And we didn't have anything better than that. And then about 20 years ago, this guy called Zweigers actually found the right definition of a mock modular form, and the theory has kind of exploded since then. And these seem to be turning up in moonshine, although my understanding is we're still at the sort of level of Conway and Norton's original paper, where you write down these functions and there seems to be something going on, but we don't understand what. As far as I know, nobody has found any good algebraic structure underlying the mock modular forms in the way that we have vertex algebras and generalized Kac-Moody algebras for ordinary moonshine. So again, that's very interesting and suggestive, but still, most of it's kind of speculative.
Great. Maybe one last question. What do you think about now? What are you working on? I mean, this was, I guess, quite a while ago. Is this something you still think about, or have you moved on?
Everybody keeps asking me that. No, I gave up thinking about moonshine about 20 or 30 years ago. I'm keeping quiet about what I'm working on now, because if I tell people, it will merely confirm that I've gone crazy. So I'll wait and see if it works first.
Thank you so much for your time, Richard. This was a true honor to talk to you about mathematics, and I learned a lot.